We're going to get started. So welcome to the 2026 Design Automation Conference, Council on Electronic Design Automation Distinguished Luncheon. I'm Miguel Silveira. I'm the current president of the IEEE Council on EDA. And 2025 is the 20th anniversary, as you can see on the slides, and this is why we're having this celebratory panel. So the Council was established to be the leading provider of technical information in all things related to design automation of electronic and embedded services, not just design automation information and tools, but also services. It was set up to foster the design automation at all levels. And the field of interest, of course, spans theory, implementation, CAD tools to design, analyze, and verify microelectronics integrated circuits. The way CEDA achieves this mission for exchange of technical information is by means of publications, conference, workshops, and volunteer activities. So CEDA is 20 years old this year, and you're at the 62nd design automation. So DAC is a little bit older, and when CEDA was formed within IEEE, it inherited DAC as an event for it to organize. And we've been co-sponsoring it for the past 20 years. Of course, DAC was not the only conference we inherited, and in fact, we expanded our portfolio. We have more than 35 conferences these days, sponsored technically and financially by IEEE Council on EDA. Besides the conferences, of course, I already mentioned the publications. We also manage the IEEE transactions on computer-aided design. We manage the embedded systems letters, design and tests, and we're also partners with other IEEE societies on computer circuits and systems for AI, signal and power integrity, and a few other publications. The Council also sponsors multiple awards, and these awards are there to recognize the contributions and the innovations of members of our community. Some of them are here that have received already awards, and some of them are here that will receive awards in the future, we hope. These include the very prestigious Phil Kaufman Award, the Richard Newton Impact Award that you saw handed out. Both of these were handed out on Monday at the opening of DAC, and also the Early Career Ernie Koo Award, which we normally hand out at ICCAD, one of our other flagship conferences. Our activities are further fostered and promoted through our more than 20 chapters set up around the world in various geographies, where practitioners and students organize events, workshops, lectures, and meet in like-minded minds discussing topics of interest to all of them. So today's panel is really a celebration of the 20 years of activities and events of CEDA, but we hope it will be also a discussion on the next 20 years, so even though we understand that that's prognosticating is not an easy task, although some people make a career out of it, but we'll see how we go. I mean, we know that the growth and the spread of computing and electronics in our lives from all facets, be it economical, social, etc., would not have been possible without the enabling presence of design automation. And CEDA is very glad to be part of this journey and an active participant on this journey, helping set roadmap for future achievements, and also fostering the training of the new engineers. And we're very happy that we participate in many student-sponsored activities at DAC and several other conferences that are extremely successful. So for decades, we've all been faced with the problem of how to deal with insatiable appetite for more that has been fueled by rapidly evolving technologies that are around us, many of which we actually enabled and fostered also. We like to think that from a design automation standpoint, we've tackled this problem in a successful way. We've innovated with tools, with algorithms and methodologies. But we know that technology keeps evolving, and faster, smaller, taller systems are just around the corner. So the problem still persists. We're still faced with the same conundrum. But now we have AI. Some would say we now have two problems instead of just one. But naysayers aside, and acknowledging how difficult it is to prognosticate and predict what will happen in the next 20 years, this panel today is going to try to tackle the questions of what's next, what breakthroughs will define the coming revolutions in AI hardware and EDA and will better ours and everyone's lives. So we'll take a stab at it with our three distinguished panelists here, which hold three axes that we see for our discussion. On my right here is Rodrigo Liang. He's the CEO of SambaNova, leading company in AI systems, offering an AI platform for accelerated inference. Rodrigo is here in place of Kunle Olokutun, who was unable to come for personal reasons, but he'll do a fantastic job, I'm sure, in his place. We also have Vamsi Boppana, the Senior VP at AMD, the person in charge of everything AI at the company, and a strong advocate of combined software and hardware optimization for powering AI data centers. And finally, of course, at the far end, before my co-moderator, we also have Alberto Sangiovanni-Vincentelli from UC Berkeley. Everyone knows him. He's a co-founder of Cadence and Synopsys, and you would not be exaggerating to say that he's a co-founder of our field in general anyway. And he'll tell us how EDA tackles the development of these new AI architectures and the changes to the structure to the AI industry. So with that, I will give the floor to our panelists, and I'll start by asking Rodrigo to expand a little bit on how he sees the next 20 years, or maybe the next few years leading into the next 20 years of AI in our industry.
I'll do my best. I'll do my best in filling in for Kunle. I think this is a topic that I think those of you who know Kunle Olokutun at Stanford, he's just very passionate about, and I think you could do a much better job articulating it. But well, I think we're certainly in this secular change where the world's moving from kind of this pre-AI to post-AI. I think we're actually going through a minor change here where we're seeing the world goes from going from a primarily training-focused world to an inference-focused world. And I think the challenge for us and on the next foreseeable future is all going to be about efficiency. How do we drive efficiency in computing? And efficiency to me means several things. First and foremost about power. I do think power is going to be the limiter to scaling AI. I think it's going to be the limiter to people being able to deploy it in production. It's going to be the limiter to getting access to computational needs in the right regions, right? Especially across the world. I travel all the time now, and so most of the world does not have power to spare at the levels that are necessary to deploy AI data centers. So I think that's going to be a vector that we have to figure out. I think efficiency also comes in the fact that the models that we're focusing on are getting, quote unquote, less efficient, right? Unfortunately. I think if you're going to see these models, they're getting bigger, right? And when they're bigger with more variation, if you look at the context windows that people want, and you look at kind of the various types of customizations and adaptations that people want, it's causing us to have bespoke models for different use cases, which means that I can't batch, right? And so when I can't batch, now you're seeing the utilization of these models get down to lower and lower batch sizes, which means that it's you're running for a manager speak, right? It's you're running empty buses, right? I've got buses that hold 32 or 64 people. I can run them only with one person at a time or two people at a time, right? So batching and that customization is driving us to less efficient computing. And then the third dimension that we're struggling with at SambaNova, or certainly very, very interested in collaborating with others on, is model variety. Right, we're seeing this multimodal world come in, and people want to actually be able to create these agents. I mean, everyone's talking about agents, but really to me it's just the interaction of lots of different types of models at a very, very fast speed. And so how do I leverage infrastructure to be able to take advantage of all these models without having to incur all the startup time and all the swap out time and all the other things that comes when you're trying to actually go from voice to text to image back to text to function calls. I mean, those are all the things that we want to do. So those are the challenges that we face, and we love to collaborate and debate with folks on what ideas there are to solve those problems.
Great. So, so Rodrigo, you gave a good overview on the application domain, on the application side of things. So Vamsi, I would request you to take it from here. Maybe you could talk a little bit about how, the applications and software that would then define, what hardware architectures we need to build, general purpose versus specialized. Are we only going to talk about data centers, or are we going to focus at the edge? And since Miguel said, we are going to look at the next 10 or 20 years, I think it's a fair statement to make that we are not going to miniaturize our transistors at that point, perhaps. Maybe I'll be proven wrong now that I'm being recorded. What the heck are we going to do about all this? So maybe you can provide some perspectives on that.
Yep, absolutely. So first of all, huge thanks and for all of you for coming and for the distinguished committee for inviting me. I think it's a huge privilege to be able to share the stage with Alberto and with Rodrigo here. So let me see, where do I begin? Look, sometimes people say, right, actually predicting the far future is sometimes easier than predicting what happens like in the near future, because it's actually counterintuitive, but it is true, right? You can
Yep.
probably call trends over the long arc of time, but you cannot tell. Certainly in my world, right, with the pace of what is happening in AI, it's sometimes like what's going to happen tomorrow is hard to call. But that said, first of all, I do agree with one comment Rodrigo made, right? That in the end, a lot of what we are doing in terms of building compute system is going to be limited by power. So that's for sure. But look, at AMD, we've been on a journey for, call it 10 years or so, building systems of all kinds, and we firmly believe that AI is going to be pervasively infused into all forms of computing, from the cloud to the edge to the client devices, right? We have the privilege of talking to thousands of customers. I personally, one of the best and most favorite pieces of my job is to engage in these kinds of conversations, and the conversations these days are all about what is happening in customers' environments as they think about, hey, here is how I used to do a traditional algorithm. Here is something that I have found where I can do it 10 times better or 100 times better because there's just a fundamentally different way of thinking about a compute problem. And they come and say, hey, how can I solve this, right? We see that, for example, in the personal computing space, we were the first sort of to bring a dedicated AI accelerator into an x86 platform. And if you plot like the compute that has been put in for dedicated AI in an x86 systems, it has, it's very steadily, right, almost to a T doubled, right? You went from some number of tops to 2x to 2x to 2x to 2x to you have today systems that are doing 50 tops of compute on a laptop, and the roadmaps clearly point to that 2x trend continuing on. So we see that happening in that space. If you see what's happening in the edge space, when 5G came along and you were looking to process 5G, we needed a fundamentally different way to process 5G. So, again, that was something where we put in an AI accelerated 5G processor, and that trend has continued on, right? The amount of processing you need in that domain. And then, of course, in the GPU, whether it's the faster supercomputers or what's happening with the language model acceleration that's going on in the space right now. So for sure, I think we see a future where the amount of AI dedicated compute that is getting infused is going to be pervasive. It's going to happen across all segments. The other piece you asked about was, hey, how do we think software is influencing these architectures and so on? It is super early innings for AI, despite what we have learned in the last few years. Just to give you an example, right? People said, hey, well, maybe I'll step back for about, 4, 5, 6 decades, right? We've done traditional computing where we've said, okay, let me tweak something and get the next 5% on an x86 processor, right? So we've actually, done a lot, but the gains were like a few percent at a time. But if you look at what's happening gen on gen with AI architectures, right? As you go from a chip to the next generation chip, we just announced our latest chip, and in certain use cases, you can get 35 times what we got in the previous generation. So the factors are not just like, small percentages anymore, but you have massive improvements that are happening gen on gen. So we're still in this very early curve. And when you are in this early curve, then, really thinking about sort of algorithms and how to impact the architectures because of algorithms is going to be so important. Like if you have a company that said, I'm going to bet on log math, because it's much easier to add than multiply, I guess, right? But then your 32 bits went to 16 to 18 to 4, then logs or non-logs doesn't buy you much, right? So you have to really be careful in terms of how you think about that. So these are some of my thoughts.
What the heck are we going to do when you run out of transistors?
Yeah. Look, well, record that. He said that.
I didn't say that. I just asked a question.
But look, I don't think we think about running out of that. Like, we've gone. That threat, by the way, has been there for a while, right? So we've gone from I don't know, when we had 1 billion transistors to now I think we have 180 billion transistors in our latest chip that we just brought out to the market. So for the near future, I think we can see that continuing on. But what is happening is, a lot of computing is also getting disaggregated. Disaggregated both at the, even in the cloud level. For example, at AMD, we've done a lot of chiplet-based packaging where we have disaggregated what sits on a single die, and things that are very close but tightly coordinated in terms of compute, delivering significant gains. That's been a piece of it. But also really disaggregated as in like it goes, to the edge and to the client, and you have a massive distributed infrastructure with intelligence, right? The world is going to have millions of models, and all these millions of models are not going to all run in one spot, right? They will run in a distributed fashion.
Okay, great. Thank you very much, Vamsi. So Alberto, now it comes to you. So there will be this huge variety of models, huge complexities. You have to deal with each one of those, right? And the architectures would be diverse. And, oh, by the way, there will be all these chiplets that are, disaggregated compute and so on and so forth. What the heck are we going to do from an EDA standpoint?
Well, I like to stand, so as a good professor, stand. Okay, so anyways, so first of all, there are some agreement that I have with my previous speakers, but I also some disagreement. So everybody says, oh, the future is all going to be AI. Now, if you look 40 years back, right, EDA conference, DAC, right, more than half of the papers were about expert systems, okay? Now, do you remember expert system? That was artificial intelligence, right? Well, how many companies do you know there still exist that were touting expert systems? 0, right? They all went out of business. Why? Because expert systems were a brute force method to try to solve problems. And so I don't know, I don't understand the problem, so I'm going to use an expert, right? That is going to be good because I look at what people have done in the past, and I'm going to leverage what people have done in the past. That's fine, but do you really understand what you're trying to do or not? If you don't, then the kind of garbage that you get is obvious, right? And so the point is that you always have to understand what is the root of what you're trying to do. And so the reason why expert systems disappeared is because we found better ways of doing that. And so we didn't need brute force anymore. And believe me, nobody could, using an expert system, could find, for example, the algorithms that were the basis of logic synthesis, right? So there was, the unate function principle. There was the algebraic manipulation and all of that, that no way that an expert system would be able to find. Now, fast forward. Now, if you look at the number of papers here, we talk about AI on everything. So AI for, making a good pasta, why not? And then AI to go to bed nicely, and then AI to place and route huge systems. Okay, but maybe not. So the point is that let's look at what are the open problems in EDA. Right? The open problems in EDA, in general, are dealing with multiple cost functions and trade-offing them one against the other. And why is that the challenge? Because it's an ill-formed problem. When you have multiple objectives, it means that you don't know which one is more important. And then you are stuck, so it's somehow, and you're looking at the Pareto optimal curve. Right? And so that is, when you don't know what you have in your hands, then a generic method like AI could work, because I don't know any better. But the moment in which I know what to do, AI understands the problem, forget it. Right? So AI in electronic design automation has a place today, maybe is not going to have a place tomorrow because it's going to migrate to higher level of abstraction. Now, the other problem where we don't know what to do is how you orchestrate different agents, right? And each agent is a place and route agent, is a logic synthesis agent, a power minimization agent. And then at this point, if you want, you have all these multiple costs, right? So performance, PPA, performance, power and area. And so that trade-offing is where I could see the use of some generic models. Now, we have done that before also, and I shoot myself in the foot because I was one who was proposing simulated annealing. Do you remember? Simulated annealing is a generic method to solve optimization problem, avoiding to get stuck in a local optima, right? Guess what? We were the best of the best in place and route using simulated annealing. Then all of a sudden, a former student of Stephen Boyd from Stanford developed convex optimization. And then all of a sudden, that convex optimization was a polynomial, powerful algorithm. And then people in EDA start saying, wait a minute, can't I cast the placement problem as a quadratic optimization problem? The answer is yes. It's not exact way in which you cast the problem, is an approximation. But then you can find it, the optimal solution. So simulated annealing, bye-bye. So brute force never works forever. Okay, this is rule number one by the professor, 78 years old yesterday, right? So, okay, so that's rule number one. Brute force never works forever. Now, if you look at the situation of AI, the model situation, right? We're talking about model, the training of the large language model, and then the specialization of that large language model for different segments. That's brute force. How many trillions parameters do we have? The latest models have more than 3 trillion parameters. Come on, guys. What is that? It's brute force. Now, what did I say? Brute force never wins. So in the end, we got to do something better, because otherwise there is no limit to the power that we are going to consume to do these things. And in fact, in design, when people are trying to find architectures to execute AI models, they consume less power. So we heard Rodrigo say 10 kilowatt, right? No, you didn't say, but I say for you.
Thank you.
Right?
Thank you.
His rack consumes 10 kilowatt, right? Now take an NVIDIA rack, it consumes 1,000 watts, something like that. Yeah, much more, okay, 10 times more, okay? So that is not going to hack it. Now, here's what Rodrigo is doing going to work. Maybe, maybe not. Why? Because you have a big, gigantic monster, which is NVIDIA, who's going to do everything known to man to match whatever the other people do. And so, I surely hope that you are going to be able to fight the big giant, but it's difficult because they have resources that nobody else has. So you have to be more intelligent, right? So you have to find new models, guys. I mean, if you look at the model that large language models use, are the original neural network model, 1950. Because then we evolved, right? We had the convolutional neural network and this and that, all gone, right? So in large language model, you have feed-forward neural networks, which is the stupidest of the model, right? So you have to ask yourself, why does it work? Why? I think that you are building a gigantic lookup table. So this is a question, this is the answer, right? That's more, 1 trillion then starts hacking along this line. You start thinking, how come you need 1 trillion, right, parameters? And then if you look at the kind of things that you get out of AI, you get very nice language, right? So the language that it answers to you and the question you ask is perfect, right? English is perfect. Now, different thing is what is written, the content, right? And then you have the hallucination, right? So sometimes you get things that don't make any sense. And in particular for EDA, we may find a design that doesn't make any sense, right? And how do we know? If you throw your brain to the AI models, you have no way of finding out what the heck it has done, and if what you have done is correct or not. And this is a real big, gigantic problem. So as long as you have a basic solution and you try to improve it, no problem. Because I know I have a fallback. And that's what is great about EDA. We have a fallback. Now, do we have a fallback to ask the meaning of the universe? We don't. And so whatever the AI is going to tell us, either we say, oh, yes, my God, or no, this is BS. But who is right? Maybe AI is right.
Thank you very much. That started off a great conversation. Okay, so Rodrigo, pushback or comments.
Well, let's see. I think as a technologist, I think it's true. I think brute force doesn't always last. As a CEO of a company that needs to make money, I love big models. I love big models. I love models that require a lot of computing. Those are hard problems. I do think. I think the world, at least in the next 5 years, is basically bifurcating. It's bifurcating into two main use cases. It's going to be these giant models, 2, 3, 4 trillion. I think that race is continuing on. I think we can. I think it's what some large companies are making their entire business around. I think it's going to be what many companies are already building their applications behind, and so I think there's going to be a race there, and whoever can run that most efficiently is going to win. I think. Faster, I think that there is a second wave that's all around these agentic solutions. So these smaller models, I don't think, my view of it is I don't think these bespoke small models that you run one individually at a time, I don't think those will last. I think those smaller models have to be in a system that runs a particular part of your overall business, because manually running a Llama 8B to do document extraction, I think that's it's such a bespoke tool that I don't think beyond the engineers, I don't think anybody's going to use. You got to do it as part of an agentic suite that allows you to do a broad range of things, and so that's going to call dozens and dozens of agents that have to be accurate. And then on top of that, then you're going to have agents to check to make sure that the original agents generated the right set of things. And so we call it guardrails, or people that are certifying the results. So you got to have an agent that's actually doing the work, agents that are monitoring the work, and agents that then making sure that you're exchanging the work properly with all sorts of different rules. And so I actually think that wave is going to transition into the market faster because it's easier to prove. For business, it's just easier to prove. For me to say this agent is doing from input A, output B, I can verify that it's doing a simple task. Now I'm going to aggregate 50 of those, and I can create a solution that I can prove to somebody that comes and says, how do you know this thing is doing the right thing? So I think it's going to go into production faster. And for that, I view it as, again, it's a multimodal. It's a multimodal model. An agentic solution, in my mind, it looks like a multimodal model where you have hundreds of these different things that are being called at different times, called in batch size 1 type of format, because you don't get to do the same thing over and over and over again. And so I think we're going to go right back into the fact that it just looks like a big LLM. Again, and Alberto is right. To some extent, we're brute forcing. We don't have better answers, so we're brute forcing it. We're trying to be elegant. We're going to try to be elegant while brute forcing, right? But that's what we got to go do. We got to figure out how to run these two use cases as efficiently as possible, and then waiting for a bright mind out there to invent a new neural net that isn't a transformer-based neural net. So we'll see what happens.
Okay, Vamsi, you want to take a crack at it, and especially, focusing on the question that Alberto pointed at, which is AI-enabled EDA. How far is AI going to, get into EDA and vice versa?
Yeah, look, I wouldn't compete with Alberto's
Go
wisdom.
ahead, please, and you're, this is your chance on video.
But I can only state a few humble experiences that we've had, right? About, 8 or 10 years ago, I think we started our first it was far from generative AI at the time. A lot of our place and route tools, because of the heuristics, because of all the cost functions that are complex and ill-formed nature of the problem, right, have hundreds of knobs. And our field application engineers, right, for specific customer scenarios used to struggle to say, hey, which knob works best for which problem, right? And so we trained a whole bunch of networks on classes of designs, and it was basically a very useful tool to, to provide, and the productivity of engineers went up quite a bit. So that was a more humble application of the problem. A more another mundane but super practical one is we have, when we tape out one of our complex chip, we have like tens of thousands of regressions we run every night. And some tests are known to be more valuable than others, right? Engineers actually get good at finding these things. So we've just trained AI systems to find the most important tests, and those run much more frequently. And the problem of how do you know they find it is solved in this case by a very simple pragmatic approach that we do run the full regression suite once a week. Right? So you will always find the problem, but you'll find problems much quicker by applying AI faster, right? So
with respect to a coverage metric, which may be very far from being perfect.
Yeah, but the point is, the choice was run all the regressions all the time, or AI-driven regressions part of the time, and all the regressions part. That actually is a very pragmatic way of applying AI. And for me, since I'm living this space, every day I think, you're like, oh, there's something I learned, right? That moment is happening so frequently. That's why I'm so bullish and hopeful about what AI is doing. Just this morning before coming to the conference, my team was showing me programming these incredibly parallel architectures is one of the most, difficult things, right? This is insanely parallel. Programming GPUs is super easy compared to almost any other accelerator architecture out there, but even GPU programming to write efficient kernels is actually not that straightforward. So we've been using AI to write AI-assisted GPU kernels, and some of the AI-assisted kernels are like beating our best human-written kernels. So we use it in that space. We use it for code assistance, right? As engineers are coding, you have assistants that are sitting next to it that are able to accelerate their work. There's just a whole host of these things that are in the AI for EDA space, more pragmatic applications. But I do agree eventually with what Alberto said, right? Just brute force solving the problems for AI will lead to dumb outcomes. Yeah.
Thank you. Go ahead. Miguel, yeah.
Going back to Alberto, so you made a case that if you have a formal way of describing a problem, or if it's formalized, then there's always at least a fallback, but typically the brute force will not work forever, right? But there are situations where you don't have a formal description of the problem. There are areas where that doesn't happen, or at the early stages, you might only have an abstract view of what you want, but you're not sure what the best way to realize it. Is there a spot there for some of these more abstract, generic, maybe let's call it brute force techniques? You want to say something about that?
So, well, as I said, there are different areas where there is still open problem in EDA, but in general in design. So one thing we said is multiple objectives, so trade-off, right? That's one. And for example, your knobs is about that, right? Yep. So because you turn this knob and then all of a sudden the tool goes faster. Why? Nobody knows. Actually, the guy who wrote the algorithm knows, but how many are there, right? So that kind of heuristic adjusting of things, sure, why not? I can envision a sort of shooting in the dark, because that's what we do with AI. We're shooting in the dark, right? We don't know, so we trust that the model, right, is going to give us an answer. So that is faith more than science. But that's okay. We don't know any better, so fine. The other area is the high level of abstraction, right? So we tried many times to do, for example, architectural design. So you give a general idea of what you want to accomplish, and then you want to design a chip that accomplishes that task, right? So you have an intent, and then you want to find an architecture. Once you have the architecture, you want to go down, you have a transistor, blah, blah, end of story. But that step is translating the intent into something is not for the faint of heart. And so why is that? Because first of all, we don't know if the intent is correct, right? We may leave out parts of the specification. So the specifications are incomplete. And there is no one who can verify if the specifications are incomplete because nobody's sitting in the head of a designer, right? Unless we use neural network to model the brain. Maybe we will be able to, right? So we transmit the brain wave into the model, and then it will say, oh, this guy wants that, far in the future. But that is one step where you try to figure out what you could do. But again, remember that whatever AI is doing is looking at data that are scattered somewhere, right? So you build out of things that happened before. So can you build something that is not there in the place where you look at? Of course not, right? So you have to base yourself on what you find in the net. So if you look at the problems where AI could have a really nice application, is combining solutions that somebody else has done and is available in the network. When we talk about automatic software writing, right? Now, what you are essentially doing, you're finding snippets of code that have been written by somebody else, very good snippet of code, and you paste them together. And that's what you do. And that's the reason why you get this fast coding, because you reuse things. Now, if you look at the publication in EDA, you have a lot of papers that talk about reuse, because it's a basic concept. I mean, I used to give a talk a few years ago where I showed that the Renaissance artists like Michelangelo were actually using things that were done by the Greeks and putting them together, assembling them. You look at the Capitol in Rome, it's done that way. So that's reuse, right? So since the man was born, we try to reuse, right? It's the best way, reuse. And so AI is good framework for reuse because it can go around internet and find out what other people have done and paste them together. Now, the problem is verifying then that what you have done is actually correct, right? And so there is a lot of discussion about how you verify code that has been written by an AI. Because yes, you can find the snippet, but then the rules that you use to combine the snippet, hey, that is not so easy, right? So sometimes it works, sometimes it doesn't. So we need to verify. Because again, AI cannot find the truth with capital T. So it uses whatever it can find. And so that is one of the challenges that I see in EDA. How do we prove that what AI is suggesting us is correct, especially in the embedded code domain. Mm-hmm. Now, I'm not talking about the hardware. We somehow have ways to verify, but embedded code is very difficult to verify because it has a connection with the hardware. So it's software, but it looks like hardware, right? And so it's kind of the worst of possible domains. And so writing embedded code is very difficult, okay? Higher level code is much easier, right? Python, I mean, I can trust AI to write Python code somewhat, right? Because Python is very simple, and it is about using, things that are already being made. It's a library, right? And that's what I think AI can help with.
Thank you. The audience has gotten impatient, as we can see. So go ahead, yes.
Impatient. Alberto, listen carefully. While you were talking, I took ChatGPT on my phone and I put Alberto Sangiovanni on artificial intelligence. And of course, I got a fairly long document talking about great things that you did in other domains and how they would link to AI. So that would make a good statement that you have been a great user and inventor in artificial intelligence. But I also remember one thing that you taught me. Don't speak with the forked tongue. And that's exactly the forked tongue. AI sometimes takes some issues and makes it in such a way that look good to you, that satisfy you. I could make a case that you're a great AI inventor, while actually your inventions are somewhere else. So coming back to the point, I think there's an agreement among the panelists that for point tools, for solving point problems like kerneling an expression, then you do need to use mathematical tools. They can be exact, they can be heuristic. To put the thing together, to do the ancillary tasks, that's where AI can come in. But the question is, you have to be careful, because putting the thing together, which is sometimes complicated, should be something good that works, not something that satisfies you because gives you something nice in form that can actually cheat you, but then would not work, which will put a tremendous work on verification. So I think that's the question. Would this doing AI for ancillary EDA tasks would in the end be good or not?
Well, again, I come back to my point of putting together things that exist. So if you have good rules to put together things and you have a way to verify, sure. And again, in my view, the large language model are very nice user interfaces. That's what it is, right? And they are a great way of searching the internet. Semantic search. So you don't go by keyword, you go by a form sentence. And large language model can parse that sentence and can give you the answer you're looking for in the network, right? So does it create something new? I don't think it's possible. It's combining things. And so sometimes if you combine things, you can find something nice, but is that really new? I don't think that, for example, AI could find the relativity and laws of Einstein. It's not there in the sense that you don't have the principles that you can use to form something that is as revolutionary as that is. So in some sense, I'm afraid that if we base ourselves on these brute force generic tools, we will not be able to reason about finding different ways of doing things, different way of formulating the problem. Because sometimes the real key is formulating the problem in a different way. Once you find the right angle and you formulate the problem in a nice way, which can be formalized, then of course you should use deterministic algorithm because you have cornered the problem. When you have an ill-defined problem, then what do? Is what Luis was talking about before. And everything which is ill-defined, then you go wherever you can find some information that will help you to solve the problem. And so being AI, the capability of searching the web. And oh, by the way, about the hallucination and things that please you, you will be surprised, but GPT-4 said that I won the Nobel Award. Nice. That pleased me no end. Unfortunately, it was not true. But that's the hallucination we're talking about. How come? Because it combined things that, like previous award and all that, and it extrapolated that I won the Nobel Award. So that's the way it works, right?
But Alberto, then you can't claim that it's not creative.
Oh yeah, that's okay.
And perhaps it's just predicting the future better than we can do.
It's extrapolating the truth. The point is that if any of you has ever done a circuit simulation, you remember that there are modeling issues, right, that you need to solve and so on. And then something is good, which is interpolation, and something is bad, which is extrapolation. Now, the problem is that when the AI gets creative, it's extrapolating. And so I won the Nobel Award.
Yes, David.
Can you please identify yourselves when you ask the question?
Yeah, so David Atienza, EPFL. So thank you very much also for the insights about the hallucinations, but I would argue that sometimes these hallucinations are maybe helpful. I mean, you have seen in design, for example, the Formula One cars that they started using AI, and then typical guidelines that we give engineers, mechanical engineers, how to do design things to be much more aerodynamic and so on. The AI came with something completely crazy. Of course, they didn't want to, but they put it in the wind tunnel and something suddenly works. So maybe hallucinations are not so bad. So the point is that you have to find ways to verify. And I agree with you how to combine that. But no, maybe going into that, cannot we find ways to actually verify what the AI is doing? There's plenty of ideas that are actually coming up on building ways to understand what the model is doing. It's of course complicated, but do you see any angles on that on the EDA, which actually much more confined problems that we combine? I mean, there are people are doing physics-induced kind of combining both. Do you see an aspect on that, benefits, working together somehow?
Yeah. Broader question, how do we verify whether AI has done anything good?
I guess, I'll take you to two examples, right? The one example is this mundane regression thing. You always have a backstop which is guaranteed to be correct, and AI is used for accelerating quite a bit of work before that. So if you always have the 100% true oracle sitting behind, then it's very easy to use AI, and we have lots of applications like that. The other one that we have found is, this code assistant kind of thing in the loop. It's actually expensive to do simulation of code, but it's not that expensive to run it on real hardware. So the AI system that gets trained has actually real hardware in the loop. And so the verification of it gets accelerated by many, many times, and you actually get much better results. So that's another type of technique that can be used. The verification, what I mean to say is, doesn't need to be like 100% better, but if it's accelerated 1,000 times in the loop, you actually get much better results.
I'd say AI in the use case of accelerating productivity of an engineer, I think that's already there. I think that's just full stop. I think if you look at kind of what an average engineer does, and I see a couple of SambaNova engineers in here, and so they'll correct me if I'm wrong. I always say, why do we need so many people, right? But I think if you look at the productivity enhancement that AI does, whether that's for hunting bugs, whether that's for actually generating code, whether that's actually for documenting. One of my big things, we don't document very well. Well, you can go through the Slack channel and start documenting very quickly. But in the end, the accountability is still on the engineer. And so I think, as a productivity tool to be able to generate 80% of my spec off of whatever code I generate or whatever commentary that we've had over Slack, I think it's useful. It's already there, but somebody's going to actually have to sit through and verify. But it's still going to be an acceleration. It's still going to be significantly more productive than somebody actually writing from scratch. And so I think that productivity part for the average engineer, especially in the chip design side, it's already there. And I think the use case on the other end of, like, say, a field engineer that's actually trying to figure out how the hell do I use this thing, right? I've got 200,000 spec sheets that which one actually uses this for this particular environment. How am I going to be able to find that in the field? That use case is also already going to be there. Being able to interrogate a company's database of spec sheets of, say, I've got this environment at 42 degrees C. In this environment, it needs to leak no more than 10 milliamps. Okay, well, which part is it, and does it have the right functions? I think that's already there as well. So I think the use cases are going to be very tight, but in the end, some end person is going to have to stand up and say, yeah, I believe the results, because like Alberto says, the hallucinations can be very subtle and nuanced, and unless you actually know what you're doing, you're going to be standing behind something that's not real, right?
Tulika, then Sharon, and then Frank. Go ahead.
Tulika,
Who are you?
Tulika Mitra from National University of Singapore. So I guess, Rodrigo, you mentioned about the bifurcation in terms of the model. So I'm kind of looking at it from system design perspective, and you said that one is like really these huge models, 4 trillion parameters. And on the other side, you are looking at agentic systems with kind of small models that are running, right? So I guess in terms of if you are designing your architecture and the system, then it seems to me that those two require very different kind of system design in terms of memory hierarchy, and both AMD and you guys are kind of really have very small amount of memory on chip. You go for like really sort of high put everything on the high bandwidth memory, and then you try to bring those things in, and then that seems to me like more suitable for the agentic AI. And then if you have like really these huge models, then I don't know, like, something like what wafer scale, what Cerebrus is doing, right? And have like huge amount of on-chip memory. That seems to be like more suitable. So I was just wondering, like going forward, what's your take on, two very different kinds of architectures for?
Yeah, so I don't quite agree with the fact that the architecture is dramatically different. It depends on how you operate it, right? And so I think if you look at the neural nets, you're bringing those sections in at a time, and you gotta manage that. But here's what I'll say. Now, I can't take credit for the data flow. If you look at kind of the way that the SambaNova architecture is done, was something that Kunle and the Stanford team, Raghu's here and folks, it really spent a lot of time thinking about it. Actually picking the right abstraction that allows you to run these things, well, that's a very large model, or genetic models, or image models. When we started, we were doing LSTMs. When we started the company, we were optimizing for LSTMs, and certainly, you got DeepSeek models showing up, and you got to operate those, right? And so our view of it is picking the abstraction layer that allows you to be able to operate these types of models is incredibly important. I think, and I give Kunle and the team a lot of credit for not overfitting, right? Not choosing a core construct that was too narrow in its application, but also not making it so free for all that you couldn't get the benefit. Now here I'll say this: the more, and we don't, I disagree with the assertion. SambaNova, we actually have a ton of SRAM. We have HBM, but then we actually have 1.5 terabytes of DRAM for every chip that we have, right? And so if you look at the memory architecture that we've chosen on our chip, I feel like the more chips I do, the more I go back to what we used to do. Right? I started building chips for servers back in '95, and we used to have L1 caches, L2 caches, L3 caches, DRAM. Right? We had that structure. We then went off and created all these different types of memory. Now we're back to basically my on-chip. I've got an L1, an L2. I've got basically an HBM that looks like an L3, and I've got a DDR directly attached to the chip that looks like you're saying the DRAM. And how you actually cache and how you actually fetch and how you actually do all of those types of things, very similar to what we've been doing for decades, right? It's just making sure that you're bringing the right set of bits and kind of where you store them. Those are the tricky parts. But I do think that you need something flexible, because tomorrow a new model is going to show up, and you're going to have to run that. Right?
Thank you.
Sharon Hu, Universal.
By the way, just Vamsi, did you want to? She addressed the question to you as well.
AMD chips work extremely well.
Okay, I need to get somebody else to come over to the microphone to
But seriously though, I think just to answer your question, right, I think we do have architectures that span a variety of spectrums, and I'm with Rodrigo saying that, look, in the near future, because of the world of models and workloads is changing so much, you do need a general purpose programmable abstraction. Otherwise, you may be locked into, right? There were companies that have tons of SRAM and no attached DRAM, and once your model doesn't fit anymore, it falls off a cliff. That would not be the right way.
Yeah, Sharon Hu, University of Notre Dame. Actually, my question is kind of more following on what you guys just said. But before that, I kind of want to make my personal observation. When Alberto started talking about why expert system didn't work, eventually died, and what's going to happen in AI, I think at the end of the day, as the EDA field, we don't care what tools you use, but if you can solve the problem well, and if you can reduce the resources, you can use less resources, solve the problem better, that's all we want, right? So in that sense, AI could have a future if we could reduce the resources. So then that comes back to the hardware design problem, right? So then in hardware design, what you guys talk about is still traditional architecture, right? Memory hierarchies. And so now there's lots of other people investigating other type of memory and other type of architectures, for example, processing in memory or in-memory computing, whatever the name you call it.
You mean analog or digital?
It could be both. It doesn't matter. Right now, there's actually two aspects. Right? One is the architecture. Can we merge the memory with computation? And then the next question is going down. How are you going to implement it? Is it analog or is it digital? I just want to hear what you guys, especially from the digital world, do you think analog has a future in this? And if yes, how about the tools?
Well, I mean, I disclose my conflict of interest, but I am the chairman of the board of a company called Innatera that does Edge AI, right? And it is, instead of being, it's event-driven, so it computes only when something happens, right? And plus, it has analog computation, right? So the power is like a fraction of the watt, right? And why do you have that approach? Is because you want to be close to the sensor. Now, what kind of task do you want to have close to the sensor? You want to condition the signal. Yep. And if you don't know where the signal comes from and all of that, you can apply an approximate model. That's what the AI attempts to do. And if you transform this model into analog and event-driven, then you can save a humongous amount of power, because then it can go on forever, right, attached to a sensor. So that definitely is very interesting to look at edge computing in that domain. But also another thing that was said before, which is very important, there are two different applications important to underline. One is the large language model and all that, fine. The other one is the model that we use to approximate a physical system. So when we don't know the equations, quote unquote, or we know them, but we want to speed up the calculation, what do? It's a black box, right? And so then we put input, we see the output, and then we fit the model. Now, if you look at 1976, right, that's SPICE Level 2 model. What was it? It was called semi-empirical model. What was it doing? It had a strong piece that was physics-based, plus a polynomial of degree n that was fitting the data. Now, that is AI, right? But it's using AI, machine learning, but it's using a different model. It was polynomial. Now we use this multi-layer model, and we don't know why this model works any better than polynomials, or the tan H, hyperbolic tangent approximation, the Volterra series approximation. Why? Well, the point is that they're extremely simple, right? And so, being extremely simple, you can compute them fast, right? But it's the same problem. You have a black box, and you want to approximate that model, and you have to fit the parameter. End of story. So the amount of accuracy that you get with that model is the same as you get with any approximation model, right? So you may as well use that, right? So it may be less powerful, but we have the GPUs that can compute it fine, right? So in this particular case, you know what you are doing. You are approximating a black box model with all the things that we know about approximating models, right? So we can find bounds in that particular case, but we can't find bounds on a large language model when you interrogate it, right? There's no physics that we can attach to it. Physics is a good thing to have, because you can verify that what you have guessed is actually the right thing. So, but, I don't know.
Thank you.
Let's hear about analog from Vamsi and Rodrigo.
So,
you guys want to take it?
Yeah, I can make a comment. So I do believe, like I said, right, in the longer arc of time, there's a real place. I mean, certainly places like sensor processing that Alberto alluded to, clearly there will be opportunities there. To say that there would be a generic computing system that can take in a wide variety of compute tasks that can all be processed in the analog domain in the near future, that I would have my doubts.
What are the most challenging parts?
I think just the practical aspects, right? First of all, let's assume that you could build a really good one, right? How are you going to program it, right? That there is an entire sort of making it operational, making it practical aspect of it that I think is not a short-term research thing, right? There is a long research problem to be solved there. even if we were able to take a class of hardware problems and abstract it to be, contained and solved through the analog space, right? That's how. In general, right, given how fast the space is moving and the tremendous amount of innovation that's happening at the algorithmic layer and above, I think there's, in the near arc of time, having a generic parallel architecture like a GPU-like architecture, a GPU architecture, which has a front-end instruction set that is relatively flexible, I think is the likely path for the near future.
Well, I would say, I mean, look, as a startup, we're always looking for that 100x. We have to, right? We have to be, the incumbents with something that's significantly better. So we're our tolerance for new ideas, new technology is extremely high, right? Because we have to, right? That said, our prosecution of whether an idea can go into our silicon is actually somewhat counterintuitive, but our first question is always going to be, okay, which fab are you running that on? Right, because if I can't productize it, so it's very quickly, which TSMC node are you running it on, right? And so it's very quickly we get down to which, and then the second question I ask is, the Synopsys and Cadence supported already, right? How do I test it? How do I integrate it? And then my third question is, okay, now tell me what value I get out of it, right? Because unless I have those first two things, as a company that wants to productize these things, I can't change the existing flow, right? And maybe another foundry can do it, but we need to understand kind of the rest of the ecosystem. What are the tools that are available, libraries, et cetera, before we can do it. And so I do think that we need more innovation. We need more ways to do it. Is it analog? There are a few things we looked at that may be promising, but again, we get stuck. We get stuck at the inability to integrate into existing designs because I rely on the ecosystem.
Well, we'll go to Frank, but before that side is winning. They're asking a lot of questions, and you guys are idling in the middle and on the right
They're saving
side,
power.
Okay? So you guys better catch up, okay?
And we're keeping tabs.
Okay, go ahead, Frank.
So great discussion on AI. To me, it feels like, given the exponentiality of everything, that everything you just discussed will be sorted out in the next 5 years, right? Given that things go so fast. So I would like to hold you to the title, the next 20 years, of what actually in 2045 you think the object is, the target is that we are going to design for, in a sense of, and we can flip the question, what's missing, what's just emerging today, what you think will be mainstream in 2045? Like, do I have to consider quantum? Do I consider MEMS, whatever, right? And just take into account, 30 years ago, my first chip was an MPEG encoder thingy. That's high-level synthesis today. 20 years ago, Alberto, we just got function architecture co-design. You did your hourglass triangles. Are those just getting broader? 10 years ago, we were like futzing around with system design and system C and things like that. But the last 10 years have been like so much faster, right? So what's missing or what's just emerging today, what will in your mind be mainstream in 2045? And I know it's a tough question, but I have a daughter in that domain. Let's see what she's going to deal with in that time.
I'm going to go last.
All my career, you pointed out the hourglass and all of that. And my point is that EDA is about design, and design has to be based on principles. And so the principle for design that I kind of distilled into, meet in the middle on one side. So you reuse pieces that you have, and you have an idea, and you combine these pieces to realize that idea. That's meeting in the middle.
No, but what I mean is really the scope, right?
No, we get to that.
Okay.
So the point is that this is a general principle. So it doesn't matter what is the thing that is on top, and it doesn't matter what the things are at the bottom. At the bottom, in the future, we may have a general compute machine that is 1 million times more powerful than what we have today. Still, I'm going to combine things to generate larger systems. And still I have an idea, and I have to realize that idea. This is not going to change. And there is always this idea of abstraction and refinement, no matter where you play. And there is always this composition, decomposition. So you have a vertical dimension and horizontal dimension. Doesn't matter what you design, it's always like that. I can reduce everything that people do into these dimensions, right? And so I can use, for example, some aspect of AI to do the composition. I can use some aspect of AI to go from, an idea to an implementation, but the principles are still there, right? So you say 2045, these principles are not going to be destroyed. It's always going to be the same because it is intrinsic in the nature of what I believe is design, right? And so if we talk about EDA of the future, it's going to be this principle applied over and over and over and over again to a certain level of abstraction. Now, if you want my honest opinion, it's likely that in 2045 we are going to have a direct interface between brain and machines, right? And so that, right. I mean, that's far-fetched, right, if you like, but that will be driving all the design by thinking, right? Okay. So that's the ultimate, right, goal. And also, I believe that we do need to understand better how the brain works, because the neural network nothing to do with the way in which our brains work. There are functions that are hidden that nobody understands what the heck is happening in our brain. But we will find out, and then what is the model of computation that our brain is using? Most likely is a combination of chemical processes and all of that. So it's a combination of analog and digital in some sense. So we go back to Sharon's question. So it's going to be analog, it's going to be digital, it's going to be a combination. And then it's going to be capturing the intent directly where the intent is formed. So that, I mean, you're already doing that, right? For people who have severe disabilities, you can connect the brains to computers, right? So it's possible. Now, right now, there is some degree of, oh my God, a chip in my brain, I don't want that. But in the future, maybe it's going to be just fine to have a chip in your brain. And then everything is connected through your brain. No more keyboards, no more big machines, So.
Maybe I'll just add one thing, right? And maybe it's a bit more of a hopeful painting of the picture. I think we are going to be in a world, certainly in that time frame, where computing will be so broadly accessible to pretty much everybody and everything out there, and that will be a significant accelerator of all kinds of positive things. I was talking to a company that specializes in drug discovery, and like Ozempic took, I don't know, 7, 8, 10 years, how many ever years in research, right? It's ultimately just a string of characters that needed to be found, and many such drugs would be found, like in the 2030s, 2040s, more drugs will be found by AI and machine-assisted operations than what humans have ever been able to create, right? So we'll be entering a world like that, so I'm super hopeful of that future.
I think in the world of computing, I'd say production computing, I think sometimes it feels like we innovate and create a lot of different ideas, and especially university like Stanford, Berkeley, these great ideas in the research side, and then you look at what actually goes on in production and what's actually dominant in the market. Sometimes it feels like the change is slower than you expect, right? And I'll give you an example around multi-core, because that's the last company that Kunle and I worked on. I mean, multi-core chips didn't really start showing up until 99, 2000, like in that time frame, in production, commercial production, right? So here we're 25 years later still dealing with multi-core chips. And so even though I think we look at kind of these step functions, changes happening in step functions, I think the semiconductor ecosystem and computing ecosystem just takes a while, because you got to drive this high level change, kind of what Vamsi said around the software programming model, the ecosystem, everything that has to get deployed, and by the time once it's deployed, no one wants to change. Right, that's the problem. Like, as soon as it's out there, now you want to, I have the next analog thing. No. I've already invested years of software, and so I think that's the reality. Kind of things go fast, and what they say with with raising kids, like the days are long, the years are short, right? I mean, same with chip design. It just feels like everything just seems like it takes forever, even though everything's changing so fast. right?
Let's go over here and then I'll come
And
to you.
then to David.
Go ahead.
Thank you. This is Mohammed Ghanem from Portland State University, and I have a very kind of generic question. So first of all, I really like what Alberto said. I feel like as a young researcher in this area, I needed to hear this. Coming to DAC, there are so many papers, so many posters that we're hoping to create so much with large language models, with AI, but we don't know if this is going to be possible or not, because like you said, it's more of a multi-dimensional lookup table, and it's just assembling things together. So my question is, when we say AI here, we're mostly talking about large language models, but there's also formal language reasoning, there's automated reasoning. And I'm wondering if you see a future where we can combine both of them to kind of make it more robust, or to use more of formal automated reasoning instead of large language models, and that maybe will be AI, not large language model based, but formal based.
That used to be called AI when I was a student, but go ahead, you guys go ahead.
You quoted something that we're doing as a research at Berkeley. So we use larger language model to interpret what people ask, to extract first order logic that is equivalent to what you say, right? And so then I can formally verify and so on. But I don't have to ask you to learn, propositional logic or anything like this. So that large language model is a great use for that, because it doesn't ask you to solve a problem, just ask you to match what you say into a formalism that you know what it does, right? So that's exactly what you say. I mean, this is a good use of large language model to translate into a formal language.
I guess we have time for one question. I had a question, but I'm not going to ask my question. Go ahead.
Yeah, so maybe just one, because I think we have a very big elephant in the room that we have been kind of dodging a little bit. Alberto touched it a little bit, that we have power constraints, power issues. So we have like two huge kind of angles. One is huge large models, bigger and bigger, consuming us a huge amount, and then which are huge lookup tables. I agree, fine. And then you have the other ones, okay, once we understand that, we create these HCI devices that are personalized and what you want to have. Don't you think that maybe in the end we should just get rid of the cloud and have these very big, very nice, interesting HCI devices that can do everything with little models? What about that?
He wants to get rid of the cloud. Let's start.
I'm just trying to see if AMD has an angle in HCI.
You mean not tomorrow, in 2045?
2045, let's do 2035 to give a margin to AMD to go there.
Okay.
Well, the hyperscale cloud didn't exist when the hyperscale cloud wasn't around in the 90s, right? So
The what cloud wasn't there.
yeah. So it was like in the 2000s. So it's not like that construct has been forever, and so I think the cat's out of the bag on that one. I do think what we're seeing though is you're seeing repatriation of workloads. So enterprises moving workloads that were on the cloud back on-prem for a variety of different reasons, cost being the primary one, but data security and privacy being the other one. So I think you're gonna see this repatriation from the hyperscale cloud may create an opportunity for us to do a more distributed computing type of environment, right? But I do think that for you to do that, you need to collapse the power, because today we're going the other way. I mean, you can only really run AI with NVIDIA on gigawatt data centers now. And so how many in the world are you going to have, right? And so we have to collapse that power by 10x, 100x in order to deploy them into distributed data center environments, which otherwise you're going to basically have not less cloud. You're going to basically be concentrating into more and more large data centers that have the gigawatt supply.
Vamsi and Alberto, the last words before we wrap up.
I think that question was tempted to extract controversy, but I leave it on a tame note. I think it's going to be everywhere. There's going to be cloud, there's going to be an edge, there's going to be a client.
But maybe don't you?
The last word.
No, but don't you think?
I agree with you. So I mean, it's a multiple level architecture. It's always been like that forever. So we are going to have a cloud with big servers and all that. We are going to have the intermediate, like for example what your business model looks like, the hardware that is going to be located in a company, and then it's going to be the edge, right? So things that are close to the sensor. Of course, that is when you deploy into drones or or brain, right, and that kind of stuff. And so edge, in my opinion, does not work in standard computing domain. The edge computing works in the embedded domain. So whatever is physical AI, we are going to have this, because otherwise, too much power. That's simple as that. So we need to be close to a plug.
Great, thank you very much.
Thank you.